Hello. So, we will continue with more approximation algorithms. So, today's first problem is weighted vertex cover approximation. Recall that we discussed the vertex cover approximation in the last lecture, and just to remind you, this is given a graph. A vertex cover is a subset of vertices such that every edge has at least one of its endpoints in this set. Now, the only twist in this case is that every vertex has a weight, and our objective is to approximate the smallest, the cover with collective weight to be smallest. So, the purpose of doing this problem is that we are going to use a technique which has many general applications in approximation. So, one way to describe this problem is writing an integer program, and here we are trying to minimize WV XV. XV will represent here a characteristic function which is 0 if vertex is not in the vertex cover, V is not in the vertex cover, otherwise it should be 1. Hence, this weight will be actually the cumulative weight of the vertex cover, and this we want subject to the following, that XU plus XV should be greater than or equal to 1 for all edges UV. This ensures that at least one of the two end vertices of this edge is in the cover, and of course, we want to ensure that X of V is either 0 or 1 for every V in the vertex set. Okay, this guarantees a meaningful value for these functions. If it is 0, then it is not in the cover, else it is present in the cover when it has value 1. So, many problems can be written in this kind of linear program, where in the discrete domain we often end up having an integer program. An integer program simply means that the values of the variable should be integral. Such programs are known to be NP hard, so we do not expect it to be solvable in polynomial time. So, what one does is one relaxes this. Relaxation simply means that we will drop this integrality condition. We will allow values, fractional values, any value between 0 and 1, and then it becomes a linear program. The linear program corresponding to this is to minimize subject to the same condition here, for all UV in E, and we replace this condition by X of V should be less than equal to 1 for all V in vertex set V, as well as should be greater than or equal to 0 for all v in V. So, this is almost the same, but now we have fairly meaningless values to these variables, because they can vary anywhere from 0 to 1. But on the positive side, this is a linear program which is known to be polynomially solvable, although in this lecture series we had discussed a solution which was not polynomial time. Recall that we had a discussion of simplex algorithm for this, but there are polynomial time solutions for this. So, we expect that we can solve this out. Then what do we do? So, then the next step is to extract vertices based on some information that we have and form a vertex cover. The vertex cover must be meaningful. There is no approximation about the vertex cover. The only approximation is that it may not be the minimum in terms of this. So, the next step is rounding. And what we do is we define x v bar as 1 if our, okay. So, let's assume that this ends up giving us some solution x v, solution is x v equal to some alpha v. This is a number between 0 and 1. So, we will say if alpha v is greater than or equal to half, 0 otherwise. Now this satisfies this integrality condition, and we are going to interpret a vertex cover as v of v such that x v bar is 1. Well, we have to show that this is indeed a vertex cover for 1, and then we have to see what is the weight of this cover and how does it compare with the optimum solution. So, these are the two steps that we have to now do. All right. So, firstly, notice that for every edge, this plus this is at least 1. So, claim 1 is that x u bar plus x v bar is still greater than or equal to 1 for all u comma v in E. Okay. And the reason is very simple, that whenever this sum is at least 1, one of these must be at least half. Okay. So, one of the two values alpha v or alpha u has to be half or more. Hence, the corresponding variable will pick value 1 in this case. Hence, this sum cannot be less than 1. What does that imply? It implies that, this implies that for every edge, one of the two endpoints, at least one of the two endpoints must be in this cover, because that is what we do. We select those vertices for which x v bar is 1. Hence, this implies that vertex covered computed here is indeed a vertex cover. Okay. So, we certainly have got an object that we wanted to compute, but how good is it? Well, so let us suppose C opt is an optimal vertex cover. Okay, so let now define ZV to be 1 if V is in C opt and 0 otherwise. So, we define this characteristic function for that set. Now, so the optimal weight of the vertex cover, that is the weight of this optimal vertex cover, is some ZV and WV. Okay. So, this is the weight of the optimum, so optimum rather than optimal weight cover. Then check this in context of the integer program we had written. This being a vertex cover has to satisfy, and it satisfies ZU plus ZV greater than or equal to 1 for all UV in the H set, and it also satisfies the fact that ZV, all ZVs belong to the set of zeros and ones. So, every one is either 0 or 1. Hence, well, it is not a surprise that this is the optimum solution of the integer program. That is, ZV is an optimum solution of the integer program. All right. Now, let us get back to this linear program. It is clear that the solution of integer program is automatically a solution of linear program, because every variable takes value 0 or 1, hence this is true. This condition is identical, and we are optimizing the same object function. So, it is clear that the optimum solution of the linear program has to be less than or equal to the optimum solution of the integer program. So, what we do is that we realized that the optimum solution of LP has in terms of the object function is less than or equal to the optimum solution of the IP, because every solution of IP is a solution of LP. Now, let us just write down this. The solution of IP sum W, the object function value was this. which from this inequality is greater than or equal to sum WV alpha V. This was the solution of the linear program. Now let us go back and recall what we did is that we picked up those vertices which had this value greater than or equal to half. So this is greater than or equal to 1/2 of sum WV rather it's not Z, it was X V bar. Notice that every value that was half or more was pushed up to value 1, but there might be some other values which are less than half which were set to 0. So this value cannot be less than 1/2 of this value. Well, this is the weight, or rather weight of the, this is the weight of the vertex cover computed by the approximation algorithm. Hence, the object function phi computed is less than or equal to 2 times object function of the optimal solution. Okay. So once again, the performance ratio is a constant here 2, and that was the same when we considered the case without weight. But the thing to learn here is that this technique is a very powerful one and is used in many cases. Okay, so second problem today is the another NP-hard problem called a set cover problem, and we would like to compute an approximation to the smallest set cover. I will begin with the definition of the problem. So suppose we are given a tuple X and a family of subsets of X, a collection of some subsets of X such that each X in X belongs to at least one such subset. So we may not have all the subsets of X, but sufficient in a way that every member of X is present somewhere. Now a cover, a set cover is a subset of F such that union C in of the sets in C is equal to whole of X, which means we want to pick sufficient members, sufficient number of sets from F such that their union covers every element of X. And the objective is to compute the smallest, in terms of cardinality, smallest such cover. Okay. So goal is to pick a smallest cardinality cover. Okay, well, as I told you, this is also a well known NP complete problem, and we do not expect that this will be solvable in polynomial time unless p is equal to NP. So, we would like to approximate the cover. Well, this time we will see that the approximation, the performance ratio is not a constant. All right. So, I will give a very simple algorithm for approximating a cover. It is the analysis which is interesting. So, let us write down the algorithm. So, approximation algorithm given f and a family of subsets of x. Okay. I will take y to be a set variable initialized at x. And the idea is simply to pick, it is a greedy algorithm, it picks that member of x f which covers maximum number of new elements which are not yet covered in the set. Okay. So, while y is not empty, and I initialize my cover to be empty. So, initially this is the cover, and then select S from F such that S intersection Y is maximum. Y will always be the set of elements not yet covered. Initially, of course, everybody is not covered. So, we pick that set from F which gives me maximum mileage in covering the elements not covered yet, and then we remove them from Y. So, Y is Y minus S, and we put that set in the cover. This is it. This is a very simple trivial algorithm. So, we want to know how good is it in terms of the optimum solution. Well, so let us do one thing. Notice that every time I pick a new set, well, notice that every time I am going to pick a new set, because if I pick up one of the old sets which has already been put in C, then I will be really having empty set here. So, it is going to pick up a new set every time. I am incurring a cost of 1 because our objective is, our goal is to minimize the size of the cover set. Okay? Our goal, we need to minimize the cardinality of C, right? That was the goal. So, what is happening is that in this algorithm, every time I picked up a set, I have incurred one additional cost. If I do that, then in my analysis, I am going to distribute that cost over uniformly over those elements which have newly been covered. These are the new elements which are covered. So, instead of taking the cost associated with S, I am going to put that unit cost on those elements which were newly covered in this. Okay. Now, let us try to define and determine rather the cost of the elements in some random set S. So, let us just say, suppose the sets were incorporated in C were S1, S2 and so on. These were the sets which actually went into the cover. Think of this as my set X, the universal set X. So, these were covered by S1, S1. These were covered by S1 union S2 as a whole. So, actually it might confuse. So, let us say these were covered by just S2. I put down here. It is perfectly possible that some of these elements are also covered by S2, but that is not so important. And say this is okay. So, the last one is say Si here. Okay. So, let us say after these elements are eliminated, this is yi. So, the value of y after I sets have been put into the cover. Okay. Now, I am taking some arbitrary set S belonging to the cover. This may or may not belong to this the cover sets. Okay. So, this is that set S, and we will see how these sets cover the elements of S also. Okay. So, this is S1, Si, maybe Si minus 1 and so on. Now, let me denote this the cardinality, the number of elements left in S after removing those covered by S1 through Si. B, we will denote that by Uj plus 1. So, these are Uj minus Uj plus 1, isn't it? Because everything up to this is Uj, everything up to this is Uj plus 1. So, this is what is covered when we selected Si for the cover. Okay. One more notation. Okay. Let Cx denote the cost associated with element x in X. What is exactly this? Well, suppose X was first time covered by Si, all right. At that time, all these were the new elements that were covered. And the price we paid to cover them was to incorporate SI. Hence, we incurred 1 unit cost. So, if X was covered by SI for the first time, then that 1 unit cost was evenly distributed among all these elements. So, if there were 10 elements in this, then each will carry 1/10, 1/10 units of cost. That would be Cx. So, what we know is that Cx, then Cx will be how much? Well, it will be 1/this, the cardinality of this section, which is y, the set here is yi minus y, yi minus 1 minus yi. So, this is 1/cardinality of yi minus 1 minus yi. Is that clear? These were the freshly covered elements when SI was incorporated, and X was one of them. They all got collectively a cost of 1. So, we distributed this much cost, 1/this much, to each of them. Hence, X also got the cost Cx, namely this. Okay. Now, with this, we are going to make one observation. Well, before SI was chosen, what we did is we checked with every set how much is that set going to cover from the remaining elements. Okay. Indeed, SI was promising this much. This very set S, at that time, had we taken S, if S is SI, then of course there is no issue, but if S was different from SI, then S was promising this much coverage, because so many elements of S were already covered, but S was going to cover this many additional elements. Okay. But we chose SI. So, even if this is same as SI, this, the cardinality of this set has to be less than equal to this number, or the cardinality of this set. Okay. So, claim is that, and this set is of course uj. We are saying that uj is less than or equal to, at best, yi minus 1 minus yi. Okay. So, let me repeat quickly. If I had chosen S instead of Si, I would have covered uj new elements. I chose to cover, I chose to incorporate Si in the cover, and that covered this many new elements. So, this couldn't have been less than this, otherwise I would have chosen S rather than this set, hence this inequality. Okay. So, from this inequality we conclude that Cx has to be less than equal to 1/uj. Okay. Now, given this, can I determine the cumulative costs of the elements of this set? Notice that this is absolutely any set. We did not particularly choose element belonging to the cover. It could be absolutely anybody. Our X belonged to this section because it was first time covered by Si. So, each of these elements have a cost same as that of X. So, sum C Z, where Z belongs to set S. You mean the total cost of the elements of S. Well, this has to be this times this, as I am looking for the upper bound at best, and that makes it sum uj minus uj plus 1. These many elements each had a cost of 1 over uj at most, and our j start from 1 and go on for all the values of the set cover. So, this is one useful inequality that we have. We will use it later on. Okay. So, now let us see how we are going to estimate the size of the cover that we have computed here. Okay. Now, one claim that is pretty trivial, if you remember how we had done the costing, is that the size of our cover, the cover that we have computed cover, is precisely sum Cx x belonging to x. Why? The reason is, every time I picked a set, I covered some new members of capital X. The cost one unit of cost that I had incurred for picking that set was evenly distributed among all those members which were covered newly from this. So, if I add up the costs of, remember that C being a cover, every member of X is already covered in this. Everybody is covered exactly once for the first time for trivial reason. Hence, if I just add up the costs of every element of X, I am getting precisely the number of sets put inside C. Isn't that trivial? Okay. Now, let us say C opt, let us say C opt is the optimum cover, all right. Now, optimum cover is a cover, hence it also covers every member of X. So, I am just rewriting this in the following fashion: S belonging to the C opt. So, this is the optimum cover. Every member of this, if you take and union them, you get X. So, this we have Cx. So, Cx x belonging to S. So, every member of this set I take, I add up their costs, and then if I add up over all the sets in C opt, I have definitely taken care of every member of X. But it is also possible that I might have taken care of some elements more than once. That may happen, and hence this is an upper bound to this. Some elements of X might be present in more than one set. So, that will be covered more than once. All the costs are non-negative. in fact all the costs are positive. So, this is going to exceed this. And then I am going to use that inequality we had for this. S is just any set, happens to be a member of the optimal cover. So, we can say this sum S belonging to C opt, and for this I have a sum j going from 1 to whatever be the number of sets in the cover, u j minus u j plus 1 over u j. This we have derived earlier, the bound for an upper bound for this sum. Okay. Now, this number is independent of S, it does not matter what S is. Hence, we can say this is less than or equal to the size of C opt times sum u j minus u j plus 1 over u j. Okay. For one thing, you notice that now you already have a situation where you can compare C with C opt. This is your performance ratio. So, let us find out what is this. So, let us try to estimate this. Of course, there is one thing that I actually did not tell you correctly, that this does actually depend on S, because these are the number of elements of S which were covered between Si minus 1 and Sj minus 1 and Sj. But we will avoid that dependence very soon, we will get over that. So, let us try to understand what is this number. Well, so let us say we write down the elements of S as element number 1, 2 and so on. Over here we have element number mod S. Okay. So, I am just looking at our definition says that this is U1. U1 is the elements that are not covered when nothing was taken into account. Then at some point here this is U2. So, these were covered by S1. So, these were this was S2 and so on. So, let us say somewhere over here we have U j plus 1 and here it is U j. So, these elements up to this, these were covered by Sj. All right. Now, what this is saying is that for each of these you charge 1 over Uj, then you will get this term associated with this section. You charge 1 over Uj for them. So, you will charge here 1 over U1, over here 1 over U2 and so on. All right. So, we will say all right, we are looking for an upper bound for this. So, we will just modify the charges as follows. We will charge for this 1 over U1. For this, we will do that with 1 over U1 minus 1 and so on. And for the last of this will be 1 over U2 plus 1, because after U2 this was the element. Now, notice that each of these numbers is less than each of the denominators is less than u1, hence these numbers are greater than 1 over u1. So, if I just add up these numbers, their sum has to be greater than equal to u1 minus u2 divided by u1. Just take a look at this term. The first term was u1 minus u2 by u1. This sum was viewed as associating 1 over u1 to each of these elements. Instead, I am associating slightly larger values, but that helps. Now, this is 1 over u1, this is 1 over u1 minus 1 and so on, 1 over u2 plus 1 for this, then over here it will be 1 over u2, 1 over u2 minus 1 and so on. Hence, j uj minus uj plus 1 over uj is less than equal to sum 1 over I going from 1 to mod of S, because this is the total number of elements in S. Such sum is known as harmonic function of at mod S. This is a discrete variant of the log of a number, because in log you integrate 1 over x dx. So, this is an upper bound for this expression, all right. So, suppose, let us say, suppose n is the maximum over all S in F for mod S, maximum cardinality among the members of F. Then, see, I wanted to avoid the dependence on S, so I am just replacing this by n. Then we have sum uj minus uj plus 1 divided by uj j, and that is now less than equal to h of n. Okay. Hence, we have mod of C equal to mod of C opt into h of n, means we have less than equal to h of n. Harmonic function, and our performance ratio is actually this hn, and this is the first time we have seen a case when it is not a constant. So, in the last lecture, that is in the next one, I am going to give you an example of a p-task, a polynomial time approximation scheme. These were actually algorithms which are giving us a fixed performance, but if you recall, in p-task you can achieve arbitrary performance, and that is where we will close this lecture series. Okay.